How many of you are here for the first time on the meetup? Wow, nice. Really nice. How many of you have seen Storm or have heard about Storm? Some of you. How many of you have actually used Storm in different setup than demo, like localhost being actually distributed? 1, 2, 3. Okay. So this presentation will be pretty much for beginners, introducing to the topic of Storm, explaining how does it work, what it actually is. I guess some of you don't know this yet. So it's a good question. What actually is Storm? I would say it's defined by who uses it. All the best companies use Storm, especially Base, and some other tiny guys like Twitter, Spotify, or you know, Base. So Storm is a thing written in Java and Clojure by Nathan Martz. It originated in 2011. In 2013, it was accepted for Apache Incubator, and already all those big guys are using it. So it's moving forward pretty fast, and it solves a pretty important problem. Some people say that Storm is real-time MapReduce. I would say it's definitely not. If you're looking for real-time MapReduce, Spark is definitely what you want. Storm is solving a different problem than running Hadoop in a fast way. Storm is for building scalable real-time processing systems. So if you have some stuff that is processed in a batch and you want a result faster, then don't go for Storm. If you want stuff that is being computed real-time all the time, then Storm is the thing. So what exactly is the problem? In the old approach of real-time message processing systems, you would have a queue of work to be done, and then a worker who would come and do the work. Now, the queue is quite important because if your worker goes down, then you want to like buffer the events and process it afterwards. And the worker is, as long as it's single one, it's fine, but it can fail, it can crash, it can be slow. So we want to scale this stuff. And the moment that you start scaling your system, you see that you need 2 introductory queues, 2 queues that will be accepting. Sorry for pointing like this. 2 queues that will be accepting data to the system. Then you have a first, maybe like this. I look nicer. So first layer of workers. They will be pre-processing events or doing some heavy calculation. They need to be distributed. They probably need to be able to take messages from both queues because maybe you have different data there. Then they will be passing their results through another layer of queues to another set of workers. And these guys will be doing different stuff. For example, you want to persist your results to the database, but you don't want like super transactional database, and you don't want to rely on single database stuff. You want to do tricky stuff and make sure that these workers don't collide with each other. So, for example, you're looking at clicks from users on your website, and you want to count how many times which user clicked. Then, if you don't want to rely on transactions on database, you just want to make sure that all the clicks from a single user go to a single worker, and then this guy receives all the messages about the single user and writes to his own cell or place in database, or his own even text file is fine because his record doesn't collide with any other. But you need to make sure that messages like this describing a particular user, they will always come to exactly the same worker. Otherwise, you will have some parts of result here, some parts of results in different worker, and merging this is a tricky task. So you definitely need your last layer of workers to be last layer of workers to have their own queues, and then to read from only one single queue for them. Now, the queue, of course, is necessary before every layer of workers, because if one of those workers dies, we don't want to lose the counts and the messages he receives. So every single worker needs a queue before them, and some of them need a dedicated queue, and some of them can use shared queue, so 2 queues for 3 workers. This gets pretty complex. Like if you take a look at the number of arrows that we have and numbers of ways you can exchange messages, this is a pretty complex system. And then maintaining this is hell, not only because it can fail in many ways, but as well, if you want to scale this up, which should be really obvious for like distributed systems, you build this to scale. Now, what you have to do if you want to add a single worker at the last column, so one guy here. If you want to add this guy here, you of course need a separate message queue for this guy because you need for every single one. So if your message queues are logical, then it's fine, but if it's physical, then you need a separate machine for this. And then you need to tell every single of those workers that there is a new queue, and you have to modify them, you have to restart all of them, you have to take care of routing of the messages. Now, if you were taking the messages and sending them, for example, by taking their ID and then do modulo 4 and send to appropriate queue, then you have to totally change your sharding algorithm, because now you have to take the values modulo 5, so you have to flash all the messages, and adding a worker is like pretty big task, and you have to go to the previous layer and modify all of the workers in the previous layer. This is definitely not the way we want to scale scalable systems. So Storm is here to solve pretty much all of those problems. In the first place, easy scalability. So if you want to add machines, you just add machines. If you want to add workers, just add workers. If you want to scale up a single part of your system, then you just add some resources to this part without having to reconfigure all of them. Sometimes you just tweak a couple variables, but the key idea is easy scalability. Then definitely higher level of abstraction. So while thinking about how the system works, where messages get routed, how to update routing, who communicates with whom, where the events are buffered, by the time you get to the business logic, you don't know what you are actually solving. So definitely higher level of abstraction. We need this. No message brokers. Like, why would we need the queues? The system should take care of what happens if some worker goes down, what happens if the message is lost, make sure that no message is lost, and give this to us for free. Guaranteed processing. So if you remember, why did we need the first message queue? This was for the case when the worker dies and we lose messages. So the system should make sure that any worker, any configuration of the death, and we don't lose any messages across the entire system. And fault tolerance, so we should get the workers who died should restart automatically and take care of the job by themselves. So all those key assumptions are fulfilled by Storm, and that's pretty much why we talk about it. So Storm is built of logical architecture on top of physical architecture, and the most basic part of the logical architecture is a stream of tuples. So tuple is any message. It's nice if it's like JSON or plain text stuff. It's easy for debugging, but if you want to send binary data of your own, you can of course convert your objects to tuples and just send them in streams. Then the streams originate in spouts. So spout is the initial part of your system, and it takes care of receiving messages from external systems, pushing it through the systems, and then if something fails, they make sure that your message doesn't get lost. Maybe they replay the message or take care of this stuff. Now, a spout can emit more than one stream of tuples, and we think of a stream as a separate infinite list of messages that come over and over again, that come one by another. So we don't expect end, we don't expect the finish of the list, they are just coming. The last part is bolt, and bolt is where the actual action happens. So bolt takes in couple streams and can produce couple streams, one or more, or none. And bolt is where all the functions, joins, filters, where pretty much all of your logic goes. So this is the calculating unit. And finally, if we take all of those and combine, we get a topology. So a topology is directed acyclic graph of which starts always with spouts, and then describes how your bolts are exchanging the messages. Now, all of the system, as we said, should be inherently parallel, and everything should be parallelable. So we don't see much parallelism on this picture, but every single of those bolts, those logical units of how the algorithm works, are translated to tasks. So we have a bolt A which does some calculation, and by design this bolt A can be split into 4 tasks which are run completely independently, maybe on different machines. Every single of those tasks can receive messages from spouts or from previous bolts, and then can emit messages to other bolts according to the system architecture. Now, if you want to scale up a single bolt, then it's enough just to add more tasks to the bolt, which is slow, for example, in your system, and Storm will take care of scaling the entire processing unit. Now, the tricky thing, if we come back to the problem of routing, so what happens if you want those tasks here in the bolt on the right to persist the messages or to aggregate the messages per user, and there is 4 of them, then there is 2 of the producers. We need another abstraction on top of this because we don't want to provide the routing rules by hand. And Storm comes with predefined stream grouping abstractions or algorithms. So every time you create a bolt, you subscribe to a stream of messages produced by someone before you, so either a spout or a different bolt. And while you're subscribing, you define in which way the messages will be split between multiple tasks. So shuffle is pick the random message, so this is easy, but it scales really nicely. Fields grouping, this is exactly what we're looking for in the case of calculating how many actions the user do on the website. So you pick a subset of fields of your tuple, and then you say that these fields there should be a hash taken of them, and then modulo this hash. The routing should send messages to your tasks modulo this hash. All is pretty nice. This is a broadcast, so every time you want to, for example, flash cache or reset counters, you want to make sure that all the tasks within Bolt receive the message, and this is where you use broadcast. And local, this is pretty nice caveat. So if we go back to the representation of bolts, every single of those tasks is a separate process, right? So they can all run on different machines, but they can be they don't have to be aligned in such a way. So you may have one task of this bolt running on the machine here and one task of this bolt running on machine somewhere else. Then the arrows don't look nice, but it works really nicely because the messages are not sent over network but locally on the same machine. And this is exactly why we have the local stream grouping. Yeah. Now physical architecture. All those things run on different machines, on different types of machines. So the master of the entire cluster is Nimbus, and Nimbus communicates with supervisors which supervise execution of the tasks through Zookeeper. So supervisors are the workers, Nimbus is the master, Zookeeper takes care of communication in the middle. Nimbus as a master, it takes the code from you when you want to upload some code to run on the cluster. Then distributes the code across workers, starts the code, monitors it, and restarts jobs if something fails. But it doesn't take care of the messages that you send. It's not his job to monitor what data is being processed or what data fails. It just takes care of machines failing and restarts jobs that were running on those machines in different place. So what happens if Nimbus fails on your cluster? Well, you cannot upload your code, you cannot redistribute the code, you cannot start and restart jobs, but whatever is running there, it's still running. You don't need Nimbus to actually run the calculation on the cluster. The second layer is Zookeeper. This is completely separate Apache project, and it's built to take care of synchronizing state of distributed system, and in Storm, it's being used for this, mostly for internal purposes and for service discovery. And finally, the supervisor, so the worker node. There are multiple processes on supervisor, so multiple JVMs. The supervisor itself, it monitors workers, local workers. In case of worker crash, it reports the worker crash and takes care of distributing code to workers. Then workers are single JVMs which do the actual work. And on single JVM, you have multiple threads, maybe a thread pool, and this is where the code runs. So if we have 3 bolts and 2 spouts on a topology, we may have 3 workers, maybe on the same machine, maybe on different machines, and the arrangement is pretty much random. The gain of this is that, for example, this spout can send messages directly to the bolt 1, and then bolt 1, when this guy wants to communicate with bolt 2, he has to either go to the first or to the third. Yeah, no, he has to go to the first worker. Then the communication is taken care for you, so you don't have to care how the messages are exchanged, but it's nice to know that sometimes you get the benefit of local execution and local message exchange. So what exactly is the processing guarantee that Storm gives us? It's unfortunately only at least once, at least the default one. At least once means every message that came to Storm will be processed successfully at least once, but may be processed more than once. So let's take a look at an example topology which starts with a spout emitting words, and then we have a first bolt which is splitting words into letters. It's emitting letters to 2 other bolts, and then first one is counting how many vowels were there. The other one is logging those messages to a text file, for example. Yeah, we will need one more extra information for this. I actually spoiled it. But yeah, pretty much everyone knows how XOR works, and if you don't, then this is a short peek. The interesting property of XOR is if you XOR the same number with itself twice, then you get a 0. So this will be useful further on. So how do we actually track the fact that the message was processed, and how do we make sure that it gets processed from the beginning to the end? There is something called Acker bolt. So the Acker bolt tracks every single message that is coming to the topology, and then every single message that is being emitted during processing of the initial thing that came out of the spout. Now, if Acker was looking and tracking every single message, it would get pretty bloated on memory. So to track, for example, this, we actually have 5 messages in the system, right? 1 coming in and then 2 being emitted to every bolt. The bigger system you get, the more messages you get. And if we were actually tracking every single one of them in this way, Acker wouldn't be able to make it on memory. So what Acker is actually doing is it's tracking the checksum of completeness of processing of the initial message. How exactly does it work? We start with a counter resetted to 0, and every time spout emits a new message, it lets know Acker that there is a new message with given ID, and it's going through the topology. Now, every time any other bolt receives a message, it lets know Acker when it finishes processing it. So every time a new message appears in the system, we get information about this, and every time a message is being processed till the end, we get a message about this as well. Now, using the XOR function, Acker is just XORing the IDs of messages appearing and disappearing through the system, and having one single counter for every message emitted from spout. It knows where every single message was processed twice, right? Every time it gets emitted and every time it gets received. So once you XOR all those values and every single message gets processed till the end, you get 0 there. And as long as you don't have 0 in the counter where you're XORing the values, you know that the message wasn't processed till the end. So let's look how does it work for the topology saying boo and then splitting boo into letters, counting letters in one bolt and then logging them in another one. So once the spout emits the message, it XORs It XORs the ID, pretty much random number, to its counter and saves the counter. And now it knows that there is something in the system. And every time new message gets emitted, so this spout will emit, this bolt will emit second B message, and we again take the new B message, XOR it into the counter and save the counter. And for as long as new messages are processed, we do this thing, and then every time message is being received by bolt and processed completely, we receive information about the message being done with. So we increase the counter in the letters bolt. We got the message that it was processed and just blindly XOR it into the checksum. After processing all the XOR values, we finally get the last message, and the last message will be the red U at the top. And once the last bolt receives the last message, we XOR the missing value to the counter, we get 0, and we're sure that it's processed. Now, how do we know, what do we do when it's not 0 for a long time? By default, there is a timeout of 30 seconds, and Storm monitors this counter for 30 seconds. If within 30 seconds the counter is not 0, so the system state is somewhere in the middle, it just says, okay, this is timeout for this tuple, and re-emits the tuple once again. This causes some problems, because if, in this case, we would drop the processing and re-emit the tuple once again, of course, both bolts would get the B message for the second time, and this is expected. You probably, if you use the raw abstraction that Storm delivers, you have to take care of this manually. Sometimes it's not a huge problem if you're just logging things, if you're monitoring things and don't care that much about how many times things happen, it's okay. If you can track IDs of messages and make sure that you're not processing the same message for the second time, it's still okay. If you're doing letters counts, it's definitely a problem. Fortunately, there are high-level abstractions built on top of Storm which take care of this problem as well. Łukasz will be talking about them. And for now, I think 5 minutes break to grab a beer, maybe use the toilet if you need. And Łukasz will continue the second part of the presentation. That's all. Thank you.
Hi, my name is Łukasz, and I work here at Base. I'm going to talk a bit about high-level abstractions built on those abstractions that Szymon mentioned before. And then we're going to move on and talk a bit about Storm cluster that we've built here at Base. Okay, so to start with, RPC, so distributed remote procedure call. Are you familiar with RPC? Who's not? Okay. Yeah, so in general, yeah, the idea is to, if we have a function which computation is very intense, we can utilize our Storm cluster to calculate this function. And it's pretty straightforward. So we set up the RPC server. This server takes a request from client. Then it attaches unique ID to the request. And then it streams this request to the spout. So the spout takes function arguments as input stream. Then the whole thing is processed by the topology. And the stream is outputted to the RPC server, which then pairs the result with the request and sends it back to the client. Pretty straightforward, I guess. Yeah, and Storm gives us some tools to build a topology like this. So there's a linear DRPC topology builder. It takes RPC name. It provides us with the RPC spout. And then it also handles returning the result to the server. And in order to deploy it, we just launch the server. It is actually packaged with the Storm. Yeah, and we have to configure those servers in Storm YAML, and then we're good to go to submit the topology. Moving on, Trident. So Trident is a high-level abstraction on top of Storm. It was introduced with Storm 08. Yeah, and one thing it gives us is a high-level abstraction language, something like Peak, to make the topology building easier. And also, it can guarantee exactly one semantic. So let's start with this high-level abstraction. So here we have our favorite words count. Yeah, so this is quite expressive, and I think it's self-explanatory, right? So yeah, so this Trident API gives us a lot of operations like functions, filters, projection. We have group by, merge, join. Those operations differ in terms of how they modify the stream. So some of them are called locally, and some of them include network traffic, like for example aggregate. And some of them are not doing anything with the data, they're just messing with the partitioning of those streams. Okay, so let's move on. Something more interesting, like exactly once. And let's have a closer look on how Trident ensures exactly one semantic on top of Storm. Yeah, so in order to do that, let's reason again on our favorite words count example. Yeah, so just to state the problem, we are here in real-time incremental world, where counts are not as trivial as in batch world, where you just take all the events and count them, right? Here we are facing, we can face failures, and also the stream is infinite, right? Yeah, so just to state the problem, we have a stream of tuples. Let's say that each tuple contains one word only. It is then processed by our topology, and we get counts for each word, right? It's all fine unless some tuple fails and is being repeated. I don't know if this red color is visible here, but let's say that this tuple was repeated, and we actually increase the counter once again, and we have a broken counter for word 1, right? So how can we deal with that? First thing we can do, we can order those tuples. So we attach some ID or transaction ID, how you want to call it, to each tuple. And then we can guarantee that tuples are updated in the database in the order of those transactions. So we cannot put transaction 3, for example, before transaction 2, right? So this actually requires to have a single point that updates the database. And in the database itself, we store the transaction that is the last transaction that updated the counter. So how it works? So we start with word 1. We say that word 1, count 1 after transaction 1, right? Then word 2, count 1 after transaction 2, and so on. And then let's move on to again, this tuple fails. And then what happens is, in the database, we already stored the information that the transaction 6 was already applied. So we don't increase the counter because we can assume that the tuple is being repeated, and the count is still good because we stay with this 3. This is fine, but this is not very efficient. So the next step is to group those tuples into batches. The idea is kind of the same. However, here when we apply count for each batch, we store transaction of this batch, and if any of the tuples from the batch fails, we reply the whole batch. So it's more efficient because the first thing is that we can actually process those counts in parallel. So each word can be computed separately, and then we can join those events in the single transactor that updates the database. And still we have exactly once, because if we already saw the transaction and applied the counter, then we don't do it again. Yeah, so that's exactly what Storm did in 07. They introduced transaction topologies, It's already deprecated, but but yeah. So what they did is they are actually handling this whole transaction, batching tuples into transactions, and they are caring for replying the whole transaction if anything goes wrong. So then we can declare this batch processing step, and afterwards we have a single committing bolt that updates the state in the database. And this trick with storing the transaction ID is actually still on developer. So in our topology, we have to develop this whole idea, right? Yeah, so this was 07, now it's deprecated, and we finally reached Trident. So the idea here is completely the same. So again, we have transactional spout that takes care of grouping those tuples into batches and applying them in order. However, what we now do is we separate the abstraction of actually counting the words and storing them. So in Trident, we have something called Trident state, and we can tell this Trident state that we want to use some persistent store. For example, it might be Cassandra or Memcached, or it might be memory as well. And yeah, and this whole playing with storing transactions ID and so on is actually done by the persistent store. So we don't have to worry about it anymore. Yeah, the writes and reads to the persistent store are all batched, so it's kind of efficient. And also, when we declare such topology, Trident gives us some tricks that some aggregations may be done locally before sending them over the network. Yeah, so this Trident state, we can use it in our topologies. We can query it. Also, we can expose it using DRPC. Yeah, and that's pretty much it, I think. Yeah, so now let's move on to storm at base. Okay, so yeah, we are proud to set up our cluster. We're using Storm on 9. So far, we have a single production cluster. It's a tiny one, but it's something, right? We have one machine for master and 2 slaves. Yeah, we also had to set up the zookeeper. And as source of tuples for the topologies, we use Apache Kafka. So let's talk about Apache Kafka for a while. Basically, it's a publish-subscribe messaging system. Actually, it's a partitioned commit log. So each partition is a separate commit log. So a sequence of ordered, immutable messages that are append only. And each message has a unique ID in this sequence. Messages are organized in topics. So, for example, I can have separate topic for, I don't know, for tweets and separate for mails. Yeah, Kafka is interesting because it retains messages for some period of time. It can be configured, and it's kind of buffer, right? We have all those messages from last week, for example, and then the offset itself is controlled by the consumer. So we can have multiple consumers reading the same topic in different places. Also, if we make a mistake, then we can tell our consumer to go from the beginning of the whole buffer. So yeah, it's kind of interesting. Okay, let's move on. So development. We are using Redstorm. It's a Ruby DSL for building topologies. It introduces JRuby on Storm. Yeah, so the thing is that when we deploy code using Redstorm, we actually include all this JRuby thingy into the jar that we deploy. So it's kind of heavy, but it works. And also Redstorm is caring for deployments. So we can just tell them to deploy it to the cluster. Redstorm itself is guys that developed it did some benchmarks, and in this concrete benchmark they calculated that comparing to the topology written in pure Java, they had 25% lower tuples per second ratio. And for us it wasn't it wasn't an issue. What we care about more was the speed of the development, and most of our devs are actually coding in Ruby. So this is kind of, probably we'll move on to some other languages in the future, but for now it's not an issue. We're not using Trident so far, although Redstorm is actually supporting it. We're not using the RPC. Our topologies are actually storing the results to some external databases, for example, Elasticsearch. And we serve reports from Elasticsearch. Monitoring. So Storm itself gives us Storm UI. So it gives us some kind of stats about topologies like uptime, workers, where those workers are actually deployed and stuff like that. We also have some stats about tuples, transferred, emitted, and it's per spout per bolt. And also it turns out that the Nimbus exposes those stats as a Thrift endpoint. So we've connected Graphite, and this is our main monitoring tool right now. So what we've learned so far. First thing is redeploy equals downtime. So it turns out that on a single cluster we can have the name of the topology has to be unique. So in order to deploy a topology, we have to kill the old one and only then deploy a new one. There is a swap on the roadmap, but it's not there yet. And as long as we do some computations in the background that can be eventually consistent, it's fine. But for example, it's probably not a good idea to use it as the RPC that is actually serving to the clients, because we can't assure the availability all the time, right? Next, resource separation. So it turns out that topologies can starve each other. So if my colleague deploys some topology that does while true, then we're gone, right? Storm itself doesn't care for resource separation, and actually what you want to do is to deploy Storm on some kind of resource manager, and there are projects that are already taking care of that. So Nathan Martz himself wrote Storm on Mesos, and apparently it's working on Twitter's production. Yahoo did some work in running Storm on Yarn, and now Hortonworks is also doing some work there. Also in Storm 082, something called isolation scheduler was introduced. Basically, it works like we can say that some set of machines can be used by only one topology, and those machines are kind of isolated from the other topologies. So it's like it's not very sophisticated, but it's something. And also it allows us to specify some lower priority topologies that can still be deployed on the same cluster, and they can still use the same machines. Rebalance. So as Szymon said, probably we can add machines to scale the storm. And when we do that, the next thing to do is to rebalance the topology. So we have to trigger Storm to actually change the places where workers are deployed, and also it often requires to change the parallelism hint for the topology. So when we're doing rebalance, we don't have to redeploy it. We have no downtime. It can be done on the fly. However, yeah, and we can specify this parallelism hint in rebalance. However, when we then redeploy our topology, we still have to change this parallelism hint in the code, right? So probably it's a good idea to have this configuration somewhere else, but we haven't done that yet. Spouts. Yeah, so we're using Kafka spouts. And as I said, the offset is on consumer, and Kafka spouts are putting their last offsets to Zookeeper. So it turns out that the name of the spout has to be unique across the cluster, because yeah, the last offset is just read from Zookeeper, and if we have two topologies reading the same Zookeeper entry, then they will kind of screw each other, right? And yeah, and we deal with that by adding topology name as a prefix to spouts names. And last thingy, correct setup. So Storm tells us that it can be fault tolerant, and in fact, when something goes wrong, when the calculation goes down, it can restart the calculation. However, we have to make sure that all the machines within the cluster can talk to each other. And we actually had a test run where they couldn't. And it turns out that Storm is he cannot do anything about it. So the computation is just timing out and being replayed. So this is something to remember about especially when we're adding new machines. Oh, and I should also mention that when we're adding new machines, all those parts of the cluster are provisioned from Ansible, so we are kind of flexible there. Yes, so summary. There are lots of parts to set up. So we had to set up Kafka, we have to set up Zookeeper, and only then Storm, right? There are issues with compatibility. So for example, when we bumped Kafka, suddenly our spout failed to read from it, and there were issues actually with those versions. So yeah, it took us a while. Yeah, but I think it was worth it, right? It's a big investment, but probably it will pay out. Other players, just a short note. So we have S4 from Yahoo. It's in Apache Incubator. There is a Amazon Kinesis service. This is also lifetime streaming, but you can also connect it with Storm. And also there's this Spark streaming. Yeah, and allow me to finish with a joke. So yeah, when we were working on it, one of our colleagues was hearing this storm all the time, and it reminded him of Sturm and Drang, of Storm and Stress, or okres burzy i naporu. Yeah, and to honor him, we named our cluster Drang. That's the story. Okay, so thanks. Any questions?
By the way of the questions, we have a couple t-shirts to give away. Really nice t-shirts, like Łukasz, can you present?
Yeah.
T-shirt, yeah, like this.
Like this.
So every question will get one, and the questions I got after my presentation as well. So
actually, mine's a bit different because it says null and I have nil. So.
okay.
Okay, so I have one. So how you can debug the false start? For example, is there any way to track the single message if it's split from the beginning to the end in case of some tumble floating or something like that?
You can turn on the debug mode, and then every tuple is logged to supervisor's logs. And also we've set up hooks on spouts, and if anything goes wrong, then we send the error to our external error tracking system.
If you run, for example, some tests, I don't know, and you, at the heavy load, you will notice some errors and you want to go back and, for example, check, I don't know, analyze the log or something like that, because you cannot really reply the full stuff. So is there any automatic tool when you can help, or is there a statistical analysis of the logs?
I would say it's logs, and also you want to have some tool like Graphite. Yeah, actually, when you deploy the topology, you lose the information about stats from that topology from the previous run. So that's also something to worry about. Yes.
You've got a transaction. I was slightly confused about what happens when a transaction uses a message somewhere in the middle. When the transaction number 2 doesn't arrive at the committer board because it lost a message, but transaction number 3, 4, 5 up to 100 have already arrived.
Yeah.
Does the committer board wait until the transaction number 2 arrives?
Yeah, it actually assures that you cannot do transaction 3 until transaction 2 is done.
Okay, so the committer board, so in case that so if the transaction 2 has lost a message, then I will, or has lost a node that was processing some part of it, and then the computer board will have to hold all the transactions that come afterwards in memory until the transaction number 2 is returned.
Yeah, you have to repeat the whole transaction 2, the whole batch for the second transaction. Okay. It's as easy as that.
So to have something like 30 seconds, something like in memory for 30 seconds plus of the input it expects.
Sorry?
To store 30 seconds plus of the input, 30 seconds plus of the input, of its input, right?
Yeah. Right.
What we're actually using is the message queue at the beginning of Storm is Kafka, and Kafka by default keeps entire week of all the messages and persists them on the disk, so you can go back by like a couple days and replay everything from last couple days. And then it shouldn't be a huge problem, because at least Storm ran on Amazon's case really well, so if you have to reprocess like last 3 weeks of data, then you just add more machines, reprocess the data, and then remove the machines. So it works pretty well.
Okay.
So you mentioned that you started the cluster here at Base. So what is actually the use case for Storm on Base? Can you review that?
I can tell you some. I mean, we're using it for reports mainly, and they are both reports to our customers and also our internal analysis. So far it's kind of those two things, but in the future we will also do some security stuff there. And
is it real time in this case, or not really? Like, do you require in this use case the real time?
It's always near real time. You cannot there's no guarantee that it will be real time. You always have this kind of delay, right? And you kind of when you decide to use Storm for some purpose, you should take this into account. Oh. No. Anyone else?
Anyone else? I have a question regarding performance. If you process mass data, what is the bottleneck? Is that I/O operation limit, rate limit, or is that CPU or RAM?
I mean, it probably depends on your task, right? Probably want to just check it. I mean, if you run out of CPU, for example, you just add machines, right? If you run out of RAM, then probably you add machines. I don't know.
You make some tests how it's scaling for more machines, because your cluster is only 3 machines. How it's scaling for more nodes?
Actually,
that comes network latency also.
Yeah. To be honest, I can't tell of any test that we did in this manner exactly. So I don't know, but you can kind of play with it, because, for example, some of the communication is done locally, right? Because you can partition the data. You can actually kind of tweak how do you partition the data, and you get some control of it.
And Twitter is publishing a lot of benchmarks, and they are running more than 100 machines on production right now. And there were data about clusters of thousands of machines, but I don't remember the results off the top of my head. But this totally depends on what you're doing. If you're doing like CPU heavy stuff, then you can totally add 1,000 machines there, and it's pretty much linear scalability. And then if you're broadcasting a lot of messages, then definitely not, and the bottleneck.
I know it's like
It depends, yeah.
Yeah.
Okay, yeah. Thanks.
I don't know if Storm is like a good tool to use it when this is a requirement. Is it possible to remove the discard some old jobs? Like if you waited too long to discard them, or for example to cancel some jobs from the queue?
Good question. So, as I remember, I'm not sure, but probably there's no built-in tool. But however, in your topology, actually you can tell the hacker or the spout to not send you this tuple again, so you can fail it permanently. So probably you can calculate it on your side, and then if you see this tuple many times and you don't want to process it, you can just discard it.
But if you have some jobs in the queue and they are not relevant anymore, you want to remove them. Like without being calculated, is it possible?
So for example, if we have Apache Kafka, we can just move the offset to the head of the queue. It's as simple as that. And we will ignore all the messages that are in the way, right?
All of them, but
yeah.
not like some additional criteria?
Actually, you can. I mean, you can just write the offset that you want to achieve into Zookeeper, right? And then when the topology starts, it will read this offset, and you can play like this, I think.
So, but they are always processed one by one. So if you want to, let's say, cancel some jobs according to the data, so let's say like you want to go through the data actually in the queue and cancel some, depending on the data?
I think you have to develop it. You have to include it in your topology. Yes.
What are exactly the problems we will meet here? Because I know problems where you've got a problem and you have some workers and you want to distribute this between those workers, but you've got here another queues from those workers to another, and this is complicated.
So you're talking about what Szymon mentioned before, right?
What are exactly problems that you solving using this stuff?
You're talking about this, or? Okay.
Yeah, about this topology, but real problems that you are solving here using this tool.
So real problems. So for example, one thing is that we like Storm because we can easily merge two streams, and we kind of, because of that, we can combine some data from different sources, and this topology is actually allowing that to us. Yeah.
I know the problem where you have only one level, and you probably send those results to something somewhere else, but here you have multi-level topology.
So, if I understand the question correctly, so I think one example could be that you have a first part that, for example, you get the email, you want to split it to words, and then you have different processors that are doing something different with those words. Does it make sense for you? So yeah, and this topology abstraction is kind of making it very easy, right? Because you just declare this first bolt, and then then it can branch to multiple streams, and each stream kind of lives separately, and it's just nice to develop, right?
So if I understand correctly, you can solve every problem with one huge worker, but if you have a split like here, and on one end of the branch you have something really easy to calculate, and on the other hand something really resource consuming, then if you have like one single huge block, accepting the tuple and then calculating the heavy stuff and not letting the fast stuff process, then your pipeline is slow. So you can split this into threads, but then you need a broadcasting system of messages, and then you're getting into the first design problem. And by splitting the smallest logical units of calculation into separate boards, you can scale every single board separately. So if you have something easy, you can run this step of calculation on, for example, 2 threads. Nobody said that Storm has to be on 100 machines. You can have like 50 threads on a single machine, but you can allocate 2 threads to the first thing, and then 48 threads to different problems. And once this grows, you can easily take this out of one machine and run on 2 boxes, then 10 boxes, and then 100 boxes without extra effort. So this gives you the fast parts are being processed fast, and the scalability is tunable per step of the calculation.
So, for example, you are running a huge task and you are monitoring this task during the execution, and you are adding workers to some parts of this topology to speed up some parts of those calculations.
Yes, but the feedback cycle is not that fast. So we're running on streams of data that don't end. So if we find that, for example, we're counting words in one stream and then doing machine learning on the other one. So we expect that the other will be like 10 times slower, but we run this, for example, for a couple of days, and we see that the other one is still slower. Then we can add 50 workers more and it scales immediately. But this is not like real-time rescaling, it's more like every couple of days we take a look, we adjust stuff.
So you've got jobs that calculates more than
like the job, the stream of events in Storm doesn't end. So you always have new users using your website, so you define the stream of clicks goes here and goes there until you grow it. So it's like running forever.
Okay, anything else? Actually, we have 2 more talks to go, so maybe like one last question and.
So actually, I would like to go back to example with you from your presentation. I don't know if it was a real example, but when you have a message distributed based on hash, and for example, you have separate workers per, for example, client which is clicking on website to count the clicks, and then you are committing to database. You don't need to have transactions because you know it's separated. So when you, for example, have heavy load and want to add some queues and workers to the system, then part of the messages are being queued. So I'm curious how it works, because when you are adding new queue, then you need to, I don't know, put some part of the messages to the new queue, or how you handle that?
Yes, you're pausing emitting new messages from the spouts. Before the spouts, there is a message queue which can wait for a while. Then you're waiting for the timeout period until all the data is flashed. You flash all the nodes, so you finish all the calculation, rebalance, and start implementing.
I see. So for the short amount of time, this actually slows down your whole system?
It completely stops part of your system.
Okay, makes sense.
Can you freeze the system during calculation?
Yes, you can pause emitting the events from starts.
Okay.
And yes, you will get addition.
Okay, so I guess we're gonna finish there, and yeah, and we are somewhere here around. So if you wanna talk to us, then you're welcome.
Pizza should be here in a couple of minutes, so I guess we will take a pizza break before next presentation. How about that?
Okay, so thanks.